I have selected the green 532 laser. You can see there's quite a bit of green light in evidence in there now. I'm quite happy to let my phone stare at the laser, but maybe not for ourselves. Okay, so we'll do a quick spectral map on here. So this is roughly the same window, but we have parameters for actually doing a map here. And so we're doing a 2-inch map, 50mm scan diameter, 1mm grid. We're going very fast at 180. The maximum is 200 spectra per second. And I'm just going to acquire like this. And then I might see if it makes any difference if I use the 850 long pass instead. So if I select that in the filter, you can probably see the filter wheel moving around there. And that's almost identical signal level. So there really shouldn't be any difference between these two filters. I guess I'll stay with this one. They will both block the green light from reaching the monochromator, which we want to do. So we will start mapping. Wafer ID is G753. And everything else will be left as is. It is indium phosphide, but I haven't programmed that material in here. And the only thing we actually use a refractive index for, or the only thing the material does, is provides us a refractive index, which we're not going to be using for this type of measurement. I already have a file for this, so I'll choose not to overwrite it. And it will move the stage to its 0 position to start from. And then this is going quite quickly. So there's a bit of hourglass effect on the map there. That's fairly normal on this type of material. It typically indicates there's some strain in the material. And I suspect there's some interaction between the strain direction and the polarization of the laser, and it gives us something that appears only on the intensity maps, but not on the wavelength map. So we've come up with an average of 1546.3. Our standard deviation is about 0.227% apparently, and our intensity of 1/3 of a volt, that's a decent signal. Anything more than 50 to 100 millivolts is a very good signal. Full width half max of 92.4, and if we go back to the other laser, we can see which one pumps the structure harder. Generally, the harder you pump it, the wider the full width half max is going to be. Same conditions, and you can see that full width half max is 150 by comparison, but this is almost at maximum power. So if I reduce this down to, maybe I'll ask for 5 milliwatts and see what we get. These lasers are usually quite repeatable, but they're not spectacularly accurate at hitting the right power. So this has dropped to 24 milliwatts like this. I'll try again, maybe 3 milliwatts. I feel like it's going to move very rapidly in this range. And we're down to 14 milliwatts here, which is broadly in the same ballpark as the other one, and our full width half max has shrunk to just under 110. So it's good and clean inside, kept in a clean room all its life. We have a white light source just here for analysing VCSEL structures for reflectivity, or we can do thickness on certain materials. We've got the 2 lasers fitted in there. We've got a number of additional slots in the filter wheel available. We have a fibre on top here for an external fibre fed laser that's no longer fitted. Those are not fantastically stable. Well, fibre feeding doesn't lead to particularly stable power. The direct launch lasers definitely have an edge there, but sometimes you need a laser that won't fit in here. We've got 2 detectors here and here on the back end of this black box, which is our monochromator, and yeah, everything seems to work.